videos while the webinar is on, and during discussion part, you can ask your doubts. I now welcome our Director and Member Secretary, sir, for your keynote address, please.
Thank you. Good morning, all the participants of today's webinar, resource person, officers, and staff of DSTE and PCS&T. Puducherry Council for Science and Technology is organizing this webinar in commemoration with the 230th birth anniversary of Michael Faraday. PCS&T is proud to organize this webinar in remembrance of the achievements of the famous British scientist, both physicist as well as chemist, Michael Faraday. His main discoveries include the principles of electromagnetic induction, transformers, and electrolysis theories. Michael Faraday, he was born on 22nd September 1791 in South London. When he was 14, he worked as an apprentice with a local bookbinder, and during his next 7 years, he educated himself by reading books on a wide range of scientific subjects. Michael Faraday is one of the scientists who never had any formal education, and whatever science he read from the books only. In the year 1812, he attended the lectures given by the chemist Humphrey Davy at the Royal Institution. He also accompanied him in a tour of different countries in Europe, which made him his interest into electricity. He also published his work in 1821 on electromagnetic rotation, the famous principle behind the electric transformer and generator called electromagnetic induction, which was discovered by him in the year 1831. During that decade, he worked on developing his ideas about electricity. He was also partially responsible for coining the most familiar words, including electrode, cathode, and ion. At this juncture, in order to felicitate the achievements, we are happy to inform you that we are organizing this webinar on Michael Faraday birth anniversary on the topic Faraday laws in fusion mesons by our expert or resource person, Dr. Suraj Kumar Sinha, Associate Professor, Physics Department, Pondicherry University, Pondicherry. Dr. Suraj Kumar Sinha is an expert in the field of plasma, which is the fourth state of matter. He is from the Department of Physics, who has contributed his work in many journals, publications, and he gained many doctorates in the field of plasma physics. He was Best Teacher Awardee in the year 2011. He also received Raman Fellowship Award and a Research Fellow at Department of Aerospace Engineering and Engineering Mechanics, University of Texas at Austin, USA. His expertise and his lecture will definitely help us to know more about the renowned scientist Michael Faraday. I hope this webinar will be useful to the participants. Thank you.
Thank you, sir. Now I request our resource person, Dr. Suraj Kumar Sinha, sir, to deliver the webinar talk.
So, good morning to one and all. I thank Department of Science and Technology and Environment, Puducherry Council for Science and Technology for inviting me. I also thank Director of DSTE&E, Sri S. Dinesh Kannan, IFS, for inviting me and giving me opportunity to speak on a very important subject which has changed our life in last 2 centuries. So I will begin my presentation.
Yes.
It should come. Share your window. Okay. Thank you.
Thanks.
So, title of my talk is Faraday laws in fusion machines. So, this is our prestigious Pondicherry University, and as I said, I thank Department of Science and Technology and Environment, Government of Puducherry uh, for this opportunity. So this is image of Faraday, and which is taken from Britannica, and the first invention, whatever Faraday carried out experiment in 1831, demonstrating induction. So he used liquid battery at the right. This is the liquid battery, sends an electrical current through the small coil A. This is the small coil A. When it moved in or out of the large coil B, this is larger coil B, magnetic field induces a momentary voltage in the coil, which is detected by galvanometer here. So it shows deflection. And this is a schematic diagram of the experimental arrangement, a diagram of Faraday's iron ring coil apparatus in simplified form. So Faraday is an example of for all of us that to do a quality research, it requires only dedication. Money, education, and other constraints cannot deter us from doing a quality research, and which contributes to improvising entire human life. So I will explain in simple way. At the beginning of this talk, I apologize from experts that it is for general talk and a few technical points has been generalized for public audience. So this is an example, a schematic diagram that we have taken a coil, this coil, and when we supply voltage through a battery or any power supply, this is symbolizing power supply, current flows through this. And there is another coil which is not connected to any of the galvanometer, so it is showing no deflection. Now, so when current flows through this coil and another coil which is separate at isolated from the first coil at some distance, and when it is connected to galvanometer, it shows deflection. That means current is flowing through this coil, induces current through second coil also. So this was very interesting one, that how electric current and electric and magnetic field interact. So the current, when current flows through this coil, it produces magnetic field, and this magnetic field which interacts with coil, isolated coil, it further generated current, and that we notice in a galvanometer and detecting the current. So now interesting is that here we see that here through this coil there are a large number of magnetic flux, but here at the secondary coil very few are reaching. So how to trap or cage in these flux so maximum number of flux cross through the secondary coil? So interesting example is iron. When we take iron and when we put it here, these magnetic field lines will be caged inside this iron core, and most of the flux will also come across the secondary. So why it happens? Let's say this is magnetic field coming out of the phase, and then we keep a iron plate here. So what happens, that magnetic field, if it is a iron is magnetic in nature, so it squeezes inside the magnetic field, and this property we utilize in casing magnetic lines of forces. So if this is a circular magnetic field here in a space, and if we put a iron rectangular iron cell here, then magnetic field will be caged inside. So this principle is used in most of the transformer what we see in everywhere around us. So this what we do is, initially there was no iron core, now we have used a iron core, so most of the magnetic field will cross through this iron core. So here when we supply current through first coil, and this produces magnetic flux which are cased by these iron bars, and again when this flux crosses through secondary coil, this shows deflection. So in general all transformers are based on this principle, and this is known as, first one is power supply, and the first coil is known as primary coil, second one is known as secondary coil, and here we can put the load. Another point is interesting is, according to our requirement, we can change the number of turns, and we can keep lesser or larger, and that will result in desired output voltage and current. So another method, rather than keeping secondary coil away, we can keep these secondary coils above this primary coils. So this is another arrangement. So this, further to understand induction, we can think of a separate arrangement where we have coil and we keep a magnet, and then this magnet which is having magnetic flux around it, when it is moved towards this coil, this produces again some deflection. That current induces current in this coil. So these are the, but this current produced in such a way that it opposes the motion of this magnet. So this is the Faraday laws. Observing this experimentally, he gave some laws, and these laws is EMF, the electromotive force produced, the electromotive force around a closed path is equal to the negative of the time rate of change of magnetic flux enclosed by the path. So it is mathematically written as electromotive force E is equal to minus d phi b by dt, that is time rate change of magnetic flux around this coil. So if there are n number of coils, we can put here n. So this flux changes and EMF may be increased and decreased with number of coils. So it is very interesting that if current is flowing across this coil, when this flux is changing, means there must be electrical field, so that electron or charge carriers inside the metal or conductor can move. So this electromagnetic force, in case of electromagnetic terms, we consider there must be a special electric field, and this electric field is in circular path, so it is mathematically represented by del cross E. So this this law of electromagnetic induction is improvised mathematically by Maxwell to give that del cross E is equal to minus dB by dt. So these Maxwell relation for a special electric field with change in magnetic field are interrelated, and that we'll see that how this law, Faraday's law of electromagnetic induction, even though it is helpful in our day-to-day life, in every transformer or electric supply which is used in our household is done, it is also useful in fusion machines. So remember, this is our diagram, a schematic diagram of induction. This is primary and this is secondary, and this is a general transformer. Remember, what we are telling is rate of change is required. So we have to give input voltage is time varying, then current will be also time varying, and if it is time varying, then we'll get also here voltage across secondary, which will be time varying, and accordingly we'll get current and turns. Here we can say some turns in primary and ns turns in secondary, and then we can get the voltage output here. So this is a general transformer. So we'll see that how this is utilized in fusion machine. So first of all, what is fusion machine? So fusion machine, it is very simple way. We have developed hydrogen bomb, and which produces enormous energy. Same manner as it is produced in sun. So it produced in sun. However, hydrogen bomb is very devastating. The question is how to control it. That whatever energy is produced, it must be controlled. And for that, nearly 40 countries, including all developed countries uh, of the world, united to form a international thermonuclear experimental reactor. This reactor is formed in is being developed in France, Cadrohas, and India is a full partner of that program. So why we are looking for this this fusion controlled fusion? Simple is, sun is an example of everlasting power station of energy. So it is supplying energy from millions of years to earth, and this energy is produced when hydrogen nuclei collide and combine to form heavier helium atoms, and this is known as fusion. So in this case, in laboratory, deuterium, which is isotope of hydrogen, and tritium, which is also an isotope of hydrogen, used to develop fusion reactor. So this fusion generator can harness energy of fusion reaction, have a special design based on magnetic confinement, and it is known as tokamak. So you can think of a bottle in which the huge energy, fusion energy, can be stored and then can be utilized for our use. So as I have said, that International Thermonuclear Experimental Reactor is world's largest tokamak and has been designed to provide the feasibility of fusion and being built by 35 nations in France, including India, on the same power that our sun and stars run. So nuclear fusion. So how two nuclei combines? So we take hydrogen, which has one proton and only one proton and one electron. So when two hydrogen atom combine, fuse together, it forms deuterium. So which has one electron, one proton, one neutron, plus it releases one positron and one neutrino. So the same thing can be seen as here, that here proton and another proton, they are fusing together and they are forming proton and neutron at the nucleus core, releasing one positron and one neutrino. So, and this is the reaction. So further, it releases, this reaction releases 0.42 mega electron volts. And once we have one, this deuterium, and then this deuterium again fuses with hydrogen and it forms helium-3. So helium-3 and emits gamma radiation plus 5.5 mega electron volts of energy. And reaction 1 and 2, they occur twice, and then it follows two helium-3 combine, it forms helium-4, which is very stable, and it releases two hydrogen and with 12.8 mega electron volts of energy. This is proton-proton cycle, and this was found by Bethe in 1938. So what we take? So if we combine two deuterium rather than protons, two deuterium, then it forms tritium and it releases 4.4 mega electron volt energy. And once one deuterium and one tritium, when they fuse and form very stable helium, then it releases one neutron and 7.6 mega electron volt energy. And further, if we take two deuterium, then it produces helium-3, which is isotope of helium, and one neutron and 3.2 mega electron volt energy. And one deuterium and helium-3, when they fuse, they also form helium and one proton with 18.3 megavolt energy. So these are the four reactions, and how to choose which one is best for using in the laboratory. So you see here that this is releasing only 4.4 mega electron volt, and this one is releasing 3.2 mega electron volt. So these are releasing very less amount of energy in comparison to both. So this is of, so using these reactions, this is atom bomb. So what we do is we put deuterium and tritium blanket outside, and to achieve very high temperature, we detonate an atom bomb here. So from this atom bomb, we achieve very high temperature, and then deuterium and tritium reaction, they start fusing, and this reaction is uncontrolled one. So to do in lab, to do this reaction in lab, we need temperature 10 to the power 8 degrees Celsius, means hundreds of million degrees Celsius for fusion. So as we have said that these two reactions, to control fusion in lab, these two reactions which are releasing lesser energy are omitted. So we omit these two and remaining with those are producing higher energy, that's 17.6 mega electron volt and 18.3 mega electron volt. However, this helium-3 isotope generating is difficult, so we also omit that. So for controlled fusion in laboratory, we have to, scientists have decided to focus on deuterium. This is isotope of hydrogen. This is tritium, also isotope of hydrogen, which produces helium and one neutron plus 17.6 mega electron volt energy. That is the most suitable reaction for fusion. So the requirement for controlled fusion is first, high density, means the number of this deuterium and tritium must be 3 into 10 to the power 20 per meter cube. So this density requirement, if this is the higher density, then probability of collision will be higher. So, and occurring fusion. Second requirement is high temperature. As we have discussed, it requires millions of degrees Celsius, that is 10 to the power 8 Kelvin. And these conditions, even if these conditions match, we need to confine this hot plasma, which is hot deuterium and tritium, for 1 to 2 seconds. And this confinement time means they must be together, close enough to fuse. So this confinement time is 1 to 2 seconds, which is very large for any nuclear reaction, during which high temperature and density must be maintained. And if we combine all these three conditions for fusion, this is known as Lawson criteria. So Lawson criteria gives, this is number density, this is confinement time, must be 10 to the power 20 second per meter cube. So this we will understand now. So for fusion reactor, what it requires? It requires first step to ionize the deuterium and tritium mixture. So deuterium and tritium are having one electron. This is, we have to make ion. So it is deuterium ion. This is tritium ion, and then they will produce helium ion, and then they will release this energy. So this means the electrons from outermost cell shall be removed. So once we remove this electron from outermost cell, and this ionized gas mixture of deuterium and tritium is known as plasma. So so now we are remain with two nuclei, which is here deuterium and this is tritium. So because they are positively charged, they will not come closer to each other. These are positively charged, so they will repel each other. So second step is required to provide sufficient kinetic energy to overcome the potential barrier. So two positively charged will repel each other, and to fuse together must overcome potential barrier. So what does it mean? So this means that if you have taken two positive charge, here it is for deuterium, this is tritium, then, and this is radius of this deuterium atom, and this is radius of tritium atom. So this is radius of tritium, this is radius of deuterium, then charge on tritium and charge on deuterium. This is electronic charge and 4 pi epsilon naught. So this potential barrier required to be overcome. So when we overcome this we see that for this it requires energy around 20 kilo electron volt. To overcome this, it requires 20 kilo electron volt, and then we can overcome this energy barrier. So for that, 10 kilo electron volt energy, 10 to 20 kilo suitable for fusion. and plasma must be hot. So let's say for general case 10 kilo electron volt is equal to 10 to the power 8 Kelvin, and so how temperature and velocity is related. So velocity square is 3 RT by m, and when we calculate this, we get the velocity of each must be 10 to the power 5 meter per second. So, and Lawson criteria 11, so it requires velocity is equal to 1100 kilometer per second. So remember, Lawson criteria says that confinement time must be 1 second to 2 seconds, and this means we have got that its speed must be 1100 kilometer per second, and if we say confinement time is 2 seconds, then does it mean that device length must be greater than 200 kilometers? So that is huge, and we cannot make such a device. So to make that, but we can accelerate, as we know that accelerate these particles between electric field between two plates. Here we apply two plates, and then this charge will accelerate, and that is the way to accelerate these particles, ions and neutrals. So another way to look into that, how to confine hot plasmas. So here, when we heat ice at 273 K, it becomes water, and greater at, when we increase by 100 degree, the water molecules become vapor and they fly away. And remember, at 3000 Kelvin, 3129 K, even iron get vaporized and it runs away. But here we are talking about that it must be 10 to the power 8 K. So even it cannot be confined in any material what we are having. So how to confine these hot plasmas? So very simple is that charged particle, they run away, but it can be confined by magnetic field. So it can be confined by magnetic field. But our problem is it requires a very long device, and this problem can be solved by a circular magnetic field. So when we apply circular magnetic field, these ions can be confined, which are very hot, which cannot be confined by any device. So circular magnetic field for longer confinement and keeps on rotating can solve our problem. So how to produce circular magnetic field? We can have these coils here, these coils, and it can produce circular magnetic field. Now, this is the tokamak design. So our plasma should be this. It should be circulating with very high speed and very high energy inside this continuously. And these are the coils to produce magnetic field, to close it, to hold these very high energy ions. Otherwise, any metal will be there, it will be vaporized within fraction of second. So these are the arrangements, and these are the some magnetic coils for correction. And here is the primary coil. So what principle is applied here is Faraday laws. Here we remember that we said when we apply some voltage, it produces flux, and this is the secondary. So it will produce current in that, and electric field del cross E. So electric field in circular magnetic field. So this principle is applied here. Here we are putting a primary coil, and this plasma, this is torus, circular plasma chamber where fusion will occur, is secondary coil. So when we flow a varying current here in this, it produces electric field in this, inside this circular chamber, and that heats the plasma, that gives energy to ions and electrons to sufficiently for fusion. And this method is known as ohmic heating, which is one of the heating, and it followed by other heating mechanism of the thing. So this is the application of Faraday laws in fusion machines. you recollect this. And there are other methods of confinement of fusion plasma. This is magnetic confinement, which is known as tokamak. This is in a stars and stars. This is by gravity, they confined by gravity, and this is inertial confinement by laser beams from all directions and to achieve fusion. So this is the ITER tokamak, which is getting built up in Cadreras, France, and I am working on plasma material interaction. You can see this arrow diverter region, and if you enlarge this, this is diverter region. So how the hot plasma may interact with this diverter region, that is my area of interest. And major fusion energy projects are in Aditya tokamak, and SST1 at IPR Gandhinagar. From the institute I have done a PhD. Then Joint European Torus, JT60U in Japan, NOVA in California, NSTX in Princeton, D3D in San Diego, and Sandia National Laboratories. So ITER is mission of various countries. It started long back in 1986, and hopefully it will become operational is 2030, and all of the younger generation can see this device can happen. So this is fusion reactor design of ITER, and so I have a video from ITER downloaded from ITER website. Can you play it? Where? Where? No, this. Open.
Video is not visible.
Yes.
That's okay. So session is open for interaction.
Thank you, sir. Even though the topic of the webinar is very scientific and tough one, so this presentation is make this webinar very simple and understandable, sir. So now I request the participants to interact with the resource person and pose questions. Please. Any questions, please? Any questions, please?
Okay. In this talk, I have just confined entire talk to one topic, that is electromagnetic induction, given by Michael Faraday, and how intelligently it is used for plasma heating. And still, it is the first technique to heat the plasmas, which is followed by then ECR, microwave, and neutral beam injection heating techniques in fusion plasmas. I have not touched upon those topics for obvious reason, because we intended to simplify this topic. So if any questions you have regarding fusion machines, that then you are welcome. Interesting point in this fusion machine is it has not been built up till now. So anybody who successfully makes it, whether it is India or any other country, they may be leader in this subject. And so it is wide open, but it requires to start fusion research programs in different parts of the country, because now earlier in 80s and 90s it was thought that it is very difficult and no country can build up a massive fusion device because of two reasons. First, none of the country were having supporting technologies. Second thing is we were not having experts. But in last 20 years, we have developed various technologies for which can be used for fusion machines. For example, we can achieve now without superconductor very high magnetic field up to 20 Tesla, and these experiments are being done at MIT now. So similarly, even different labs or universities may focus on this project because cost has gone down. So if any question is there, you are welcome. And thank you. I thank all of the participants for attending this lecture. And once again, I thank Government of Puducherry, Department of Science and Technology and Environment, Puducherry Council for Science and Technology. I also thank the Director of Department of Science and Technology and Environment, Sri Dinesh Kannan, and my friend Shiva, and all other officers. Those have made this event successful, especially Sri Sagai Alfred, Dr. R. Sagai Alfred, Senior Scientific Officer, DSTE, and all other members of this Department of Science, Technology and Environment. Thank you.
Thank you once again, sir. Sir, one question is there in the box, sir, please.
Thank you, Swarnev, for this interesting question. Commercially, it is now 22 Tesla. It is available and it is repeatedly generated in smaller devices. Smaller than those are not very small. We can do fusion experiments on that. So this is the answer.
So any more questions, please? So thank you once again, sir, for wonderful presentation. It's time for vote of thanks. Now I request my colleague, Mr. Sivakumar, to extend vote of thanks.
Thank you, sir. Thank you, Dr. Suraj, for a wonderful lecture on the occasion of 230th birth anniversary of famous British scientist Michael Faraday. His contribution was remarkable to the mankind, who was brought to limelight by our expert in this webinar. We learned a lot about the application of Faraday's law in the fusion machines which we are using in our daily scenario research like CERN and tokamak. Thank you, sir. On behalf of our secretary cum chairperson, I thank our research person and our member secretary, senior scientific officer, and all participants for making the webinar great success. I hope this webinar is very much useful to all participants about the Faraday's laws. I further request all the participants to kindly fill the feedback form to get each certificate. Thank you all.